colleagues, researchers, and organizers of the conference. Today, we are here to present our work on the development of IoT-based model for water optimization paddy fields. And we have our team here with the current following members on the screen. Due to the time constraint now, I'm directly moving on to the introduction. So our aim of our project was to help in creating awareness about the mismanagement of water in the paddy fields by determining and alerting farmers on the water level that is required during various stages of the paddy growth. So we wish to achieve this by providing a real-time monitoring and prediction system for the farmer so that they can quickly respond to any significant change in the paddy fields. And also our ultimate aim is to help them slowing down the groundwater depletion and produce more yield. This is a pictorial representation of the huge water losses that occur in the one periodic cycle of a paddy growth and how it accounts with the needs of the 250+ rural houses across India. So main objective of our project is to assist farmers in adopting appropriate water management techniques for paddy cultivation. And second is to provide an early warning system for paddy farmers to prevent flooding and to check for water misuse in the paddy field. These are the ways, the three electronic components that we used in our product, and we will be further discussing it in the following context of the presentation. So we have here the LoRa, which is a wireless communication motor, which uses a radio frequency to transmit the data, the programmable e-speaker device, and also the time-of-flight sensor. So in order to achieve our objective, we have developed a four-step methodology. The first one is an on-field water level. So it's a basic model which consists of the ESP device and the time-of-flight sensor to determine the water level in the field itself. The second one is an on-field water level. So it's an advanced model, the advanced model of the basic model, and which integrates this LoRa so that the values can be sent directly to the farmer's mobile. And third methodology is a warning system. So it is programmed such a way that if the water level is surges or diffuses to a certain point, a warning system, a buzzer is activated in the home unit device, and it will allow the farmers. And the fourth methodology is an application. We have developed an application for the farmers to guide them in the irrigation process on the various stages of paddy growth. We have used the Tangible software for this building for developing our mobile application. So this is our proposed solution of project. So here, the field unit will, with the help of the time-of-flight sensor, it sense the water, read the water level, measure the water level in the field, and it transmit the data to the home unit, the device, using a LoRa module, which uses the radio frequency to transmit the data. And from the and in the home unit, the values are the readings are then stored in an online cloud database. So here we use the Google Firebase, and then the mobile application will retrieve this data from the Firebase. So these are the two designs that we developed, two models that we made using the Fusion 360 software. The first one is a normal field unit. We can this model can be developed to be used in areas where the irrigation techniques are not used, water management techniques are not used. And we can divide this this model into three parts. First one, the top portion is the component casing, which encloses all these electronic components. The middle portion is the cylindrical portion, and the third and the bottom portion is the three legs, which stabilize the entire product on the field. And the second one is the field unit for AWD. So it is just only the component casing, which encloses the all these electronic components. So in the paddy fields which adopt this alternate wetting and drying methods, we can see that a tube will be based on that field, which adopts this AWD technique. And we can place the component casings over the existing tube on AWD tubes in that field. And these are the field and home unit displays. So the field unit, we can program in such a way that if the farmer wants to manually check the water level in the field itself, then he can check using these various buttons. And in the home unit, we have a program such as if the water level is in a desirable range, that is, if the water level is in a perfect condition, then if the field is in perfect condition, it will gives a green color screen on the display. And if the water level suddenly surges or decreases at a certain point, it will give a red, and it starts to give a red screen on the display, and also a buzzer gets activated, warning the farmers. Moving on to the working of our application, mobile application. So like I mentioned in the methodology. So first we have the begin screen. So the begin screen, we have the begin button, the community icon, and also the refresh button. So if the person is a first user, then you have to go through a questionnaire screen where one have to provide the information of the area, the location, the area, the name, and the farming type they're using. And after that, it will move to a speaker screen that here we name it as an AW screen. So in this, the screen will help the farmers in guiding them to guide them in the education process. And also you can see a remark portion at the bottom of the screen that do not irrigate on row. So if the water level, in the irrigation, if the water level, we are pumping the water into the field, if the water level is in the desirable range, then it will give a remark of perfect. And if the water level is water level starts to increase beyond a certain point, it will start to give a remark of do not irrigate. And if the water level in the field is below a certain point, then it will start to give a remark of please irrigate. And we also indicated the weather screen in our mobile application. We also provided a community screen portion, which is a social platform for the farmers to convey to post their doubts, their problems they're facing, and the experts can answer it. They can provide a solution to these problems. And moving to product testing. So here we had to simulate various rainfall conditions and keeping in our mind the COVID scenario and the weather patterns in our region, especially Kerala. So we also made simulation on the water level for various states of the PADDY crop. So this is a temporary model that we made due to this lack of material because of these COVID situations. And here we use a PVC pipe of length 28.4 centimeter and diameter of 9 centimeter. And a parasitic was used for enclosing this electronic components. And the water level was basically regulated and monitored. So for testing purposes, we used two methods of irrigation. The one was a general method of irrigation, and other was the alternate wetting and drying method. For general method of irrigation, we take the time duration of testing was around 6 hours, and starting from 9 a.m. to around 3 p.m. In the evening. So, and data was transmitted regularly at a 1 hour interval. And we also, the app remarks were used to check these are various ratings that we got while doing our testing. And the app remarks were used to check if water level was perfect, or if it needed for the irrigation, or to completely stop irrigating if there is any overuse of water. So in the AWD method of testing, in the AWD, that is alternate wetting and drying method. Here, first of all, we have the time duration and the time interval was same as the previous method. And here, the water level was maintained 5 centimeters above the ground at first, and then we are allowed to gradually fall it to around 50 centimeters below the ground level. So when we have maintained the water level, and when we have maintained the water level in the desirable range, it gives a app remark of perfect. And when we increase the water level, then beyond a certain point, it starts to give app remark of stop irrigating. So, and when we maintain the water level below the 50 centimeter down, we got a app remark of please irrigate. So by getting this app remarks on all, the farmers can understand. They can it will help them guide in the irrigation process and all. So this is a video animation of how our product works. So consider this is a paddy field, and here we are placing our product on the paddy field. This is normal field unit. So which consists of this LoRa, the time-of-flight sensor, and the programming ESP32 device. And here the data is sent to the home unit, which consists of the programmable ESP32 device and the LoRa unit. And here, if the water level is in a desirable range, it will give a green screen. Then if the water level is not in a desirable range, it will give a red screen, and a Basil gets activated. And the data are then stored in an online cloud database, and then the mobile application will retrieve this data from the Firebase. So this is a conclusion that we made. The initial stage of our product development was successfully concluded, and transferring of water level measured using time-of-flight sensor, and the data were successfully stored in the Firebase. And the real-time water level was monitored using the field and home units, and was represented on the screen displays of the device. And the simple app representing various water levels during various stages of paddy growth was also developed, and we have calibrated our time-of-flight sensor and this is reading accordingly. Thank you. Thank you,
Rohan, for your